Good morning. In the last class, we were discussing about error involved in the current transmitter stage of 420 milliampere current transmitter. So, if you recollect, basically what we are trying to do is we are trying to transmit the signal in the form of current. So, for that we had the input stage as a voltage regulator. So, we had a voltage regulator at the input, then we had followed by that we had a current transmitter. So, we had our voltage regulator like this, and then we had to start we had the Zener diode like this, then followed by this we had the current transmitter here. So, this was we had shown as 6.25 K and this was 6.25 K and then 5 K part was used. Then this was actually connected to this. Then we had the output current converter stage. So, this is actually given as a feedback. And this was used as a zero adjustment, this is used as a span adjustment. So, this is the current transmitter which we were discussing, and then we also calculated where is error that used to come because of temperature drift. So, we calculated what is the error due to the offset voltage drift of this op amp, then these resistance change, then what is the error that you will get in the voltage regulator. Then similarly, if the Zener drifts, then this output voltage changes, then what was the error that is coming, because of that you have calculated. And then we also calculated what is the error that comes because of the offset voltage drift of this op amp. Now, we have to calculate what is the error due to this, and then other errors, that is what is the error due to the drift of these resistors. Now, we can do many things, but I will calculate only one case, that what is the error that comes due to this resistance drift. The rest that you can do it yourself. So, if you take this example that we have taken, this is a 235 ohm resistance, this is a 235 ohm resistance we have taken. Let us see, and this was normally around 10 K and this is actually 470 K and then 470 K. Now, let us assume that this resistance is drifting due to temperature, and then what is the current drift that you can expect because of the drift of this resistance. So, we calculate the current drift due to drift in, say, this resistance R7, drift in R7. Let the temperature coefficient of R7 is equal to 50 ppm. Assume that we are used at 50 ppm per degree C resistance. Then for 100 degree C, delta R will be this is 235 ohms. So, 235 in 50 ppm, and then for delta T is equal to 100 degree change, then that has to be 100. So, that is the resistance change expected, that will give you 235 into 5 into 10 power minus 3. That is what that because this that amounts to in 1.15 ohms actually. That is, the total change will be 1.175 ohm resistance change expected in 230 ohm resistance when temperature change of 100 degree occurs. So, what is the corresponding current change? Now, the 1.175 ohm change in resistance here, if we take this, if the, for example, if the resistance in this case, if it goes up, then this voltage will go up, and then this goes up, then automatically the current will go up, then current have to come down, because if this voltage goes up, this voltage will come down, the current have to come down, such that original value is maintained. Because essentially this voltage at this point and voltage at this point have to be same all the time. So, eventually if 1 millivolt 1 ohm resistance changes here, then that will be a change in voltage, and that voltage, half of that will be appearing here. So, it has to correct it back such that again the current decreases, so that the original voltage is retained back. So, we can calculate the current change, and that depends upon what is the actual current that is flowing. So, easiest way of doing this would be assuming that around 16 milliampere current is flowing at the maximum. So, 235 ohm gives you 16 milliampere current, then 1 ohm what is the current that it gives, that would be easier route to find out the error due to the resistance change. So, what we do is we will take assuming 260 milliampere current is flowing, because normally you have 20 milliampere current, of which 4 milliampere current comes from the other part of the circuit. Normally the current through this will be around 16 to 17 milliampere. So, we assume here it is 16 milliampere current. Assuming 16 milliampere current in R7, then for 1.175 ohm change, the expected current change is that would be 16 divided by 235 into 1.1 ohms. That will be roughly about 17.6 divided by 235. That actually, if we take percentage wise, okay, that will be in current in milliamps, that will be in milliamps. So, that will be 51 by 15, that you will get approximately milliamps, that will be 0.06 milliampere current. So, because of that resistance change, the R7 change, you will have a current drift of 0.06 milliampere. Like this, the various errors in a circuit can be computed. I leave the rest of the error calculations to you, so that you can practice that and arrive at total error involved in the circuit. Now, let us see at another design, namely how to use LVDT for displacement measurement. So, we will pick up another example, that is design of LVDT based position transmitter. So, if you first we will explain what is LVDT. So, if we take LVDT, this is actually a linear variable differential transformer. It looks like this, that is, you have a primary and then you have two secondaries associated with that, and then you have a core which is moving core is there. So, the idea is that if I energize the primary with AC voltage, then you will get a voltage here V1 and then V2. Now, if this core is in the middle, that is linking half of this coil and then other half is linked to this coil, then this voltage V 1 and V 2 will be equal. In case if the core moves up and if the core occupies more of this and then less of this coil, then you will have V 1 more and V 2 less. Similarly, if the core move downwards, then it will have V 2 more and V 1 less. So, if you want to realize this in 3 dimension, then this looks like this, that normally there are no LVDT as a core bobbin is there, and then you have a 3 segments. In this actually one secondary is wound, and in this another secondary is wound, and the primary is wound in the middle. So, this is the primary. So, here it comes primary and then S1 and S2 two secondaries. So, this is coming S1 and this is S2, and the core is actually normally moves inside. So, you will have the core inside. If you see, it will be like this. So, that is the core that it comes. So, the movement of this core, if I take another color and so you see the core will be this. So, now for example, it normally when the core moves, if the core moves, you will have all the time primary will be linked to the core. If the core moves for example towards this, then you will get the core will be mostly occupying S1 and then the primary, and secondary will have very little link to the core. Or if the core moves this way, then you will have the S2 links the entire core and then primary, there is no linkage to the S2. So, that is what it happens in this case. So, we are shown schematically like this. You can physically the LVDT looks like this. So, essentially what is done is that they link this one for the displacement that is to be measured, that is mechanically connect this to the system where the displacement to be measured. So, when there is a displacement, then core moves accordingly, and accordingly you will get more voltage in V 1 or V 2. If it links both the coils equally, say if the core is at the middle, then you will get V 1 and V 2 equal. So, by measuring V 1 and V 2, one can determine the position of the core. This is the purpose of LVDT. That is why this is called linear variable differential transformer. So, now mostly the V 1 minus V 2 difference linear for the displacement up to a certain range. For example, if we take a 3 mm LVDT, then for a 3 mm displacement of 3 mm displacement of this core, you will find V 1 V 2 difference is linear. So, this is the basic principle of the LVDT. Now, we see how to use this for position information, and then what are the errors associated with this, and then how to take care in the circuit design. So, if you look at this, if you look at the basic LVDT, then what are the problems associated with this? First thing is I had to energize this with the AC source, and then I have to pick up these voltages V 1 and V 2, the two voltages. Now, the problem is that when the core moves, the amplitude in V 1 and V 2 changes, but in addition to that the phase relation between the primary and secondary also changes. So, actually if you want to really see the difference, you only have to see the magnitude of V 2 and the magnitude of V 1 is the difference that we have to measure, that gives you the displacement. That means I have to rectify and make it DC, this also I should rectify and make it DC, and then the difference between these two DC voltages will give me the displacement. That means what I have to do is I have to convert V 1 and V 2 into DC. This DC voltage difference this DC voltage difference alone give you the displacement, not the AC voltage difference. So, this is one problem. Then second problem is when the LVDT is used in the actual in the field, invariably you will find that the temperature of the entire unit changes. Now, we have issue with that, because if the temperature of this changes, then the coil resistance also changes, because this primary, for example, if we take this is having a resistance, because LVDT wound in a smaller size and they use a very thin wire. So, the resistance of this coil matters a lot, because whatever voltage is there, whatever applied voltage is there, that is partly applied on the that is partly lost on the resistance of this wire. So, if I take the LVDT, that it has a resistance in the primary and as well as inductance, only whatever voltage is there and the inductive part alone transferred to this and this. So, whatever voltage there and the resistance is not transferred, it is a loss. So, as the temperature increases, this resistance increases, and consequently that you have less voltage across this, even if the applied voltage is constant, and you will get reduced voltage in V2 and V1 proportionally, and that makes V2 minus V1 difference also changes with temperature. So, essentially if you see the for a given position, you will find even if this is constant, the difference between V2 minus V1 changes with temperature. This is because, as I said, because of the temperature change, mostly the resistance of the wire changes, and that creates problem. So, this is the second major problem that one have to solve, that is essentially V2 minus V1 changes with temperature also. Changes with the temperature. So, these two problems are to be solved if it is to be practically used for displacement measurement. Now, let us see how to tackle first the temperature. Because of temperature change, we are losing some voltage on this. How to tackle this problem we see first, that means we have to make V2 minus V1 independent of temperature change, then only displacement measurement possible. So, we solve this problem first, then we go and see how to make V1 minus V2 DC, and then the DC voltage must drive a current source, more like 420 milliampere current transmitter also need to be built along with the LVDT. So, first step would be how to make V2 minus V1 independent of temperature, Now, because of temperature, the resistance of the wires change, because of that we are getting error. Now, to solve this problem, normally what is done is, we know that if V1 plus V2, suppose if I take V1 and then add with V2, the total voltage V1 plus V2 supposed to be constant in the LVDT. This is because when we are moving the core, if you see our original discussion, when we are moving the core, V1 is increasing and V2 is decreasing. For example, if I move in the core upwards, then V1 is increasing, V2 decreasing. But if I find V1 plus V2, that will be always constant. Similarly, if I move downwards, then V1 will decrease, V2 will increase, and again V1 plus V2 will be constant. So, if I make V1 plus V2 constant all the time, then that will I need not worry about the temperature drift at all. So, what is done is that you take V1 and find DC, and V2 you take and find a DC value, add these two and compare it with the reference, such that by varying this voltage, for example, if the temperature is going up, then the resistance of this goes up, and then I will get V1 less and V2 also less. Now, to get back old value, then I increase the excitation voltage of this. I increase this voltage. If I find V1 plus V2 is reduced because of temperature increase in temperature. So, I can alter the excitation voltage. If the voltage here V1 plus V2 comes down, then I increase the excitation voltage. If V1 plus V2 goes up, then I decrease the excitation voltage. So, that always V1 plus V2 will be kept constant. So, essentially what we now we do is we will rectify and convert V1 into DC, V2 into DC, and then add these two voltages. So, that we will get V1 plus V2, and then we compare it with reference to get constant. So, if I draw the block diagram of our proposed scheme, it will look like this. That is, what I do is I will take the two voltages V1, and then I make it DC, rectifier I put, then I will get a DC voltage here. Then I take V1 here, then this is the core, then this is the primary. Similarly, I rectify this V2, then I again get a DC voltage. Now, I take these two voltages, then add these two voltages. For example, I can add these two voltages here. I put this, I added these two voltages, then I compare it with the reference here. For example, this is supposed to be minus, you have minus. So, this I compare it with the reference voltage. So, this I give it to V reference fixed voltage. This output I connect to oscillator. Here is the oscillator circuit. The oscillator drives this LVDT primary, this is primary of the LVDT, and this is S1 secondary 1, secondary 2. Now, this will control the oscillator output. So, that the amplitude of the sine wave oscillation is changes depending upon the output of this error this comparator. So, what is done is here we get V1, here we get V2. So, at this point I will get V1 by 2 plus V2 by 2. If I put this equal resistance here, then I will get at this point I will get this, that is nothing but we added the two voltages. Of course, we are divided by 2, does not matter. So, now we compare with the fixed voltage. Suppose if this is a 2 volt, if the amplitude of the oscillation is less, then and if this is lower than 2, then the output will go high. The output goes high, then it will increase the amplitude of the oscillation here. So, if the voltage increases here, this also will increase, and the oscillations will be more, and you will get increased V1, V2, and again this and this will increase, and that will make this voltage to go high. So, in case if this is lower than 2 volt, if it is more than 2 volt, if this voltage goes more than 2 volt, then output will reduce, and then amplitude will reduce, and then this will reduce, and then eventually this also will come down. So, at any given time if I do this, this voltage will be equal to this voltage. So, it maintains voltage at this point V1 plus V2 constant. That means, even if temperature changes, if the resistance increases, then what happens is this voltage will decrease, this also will decrease. That will make this voltage to go high, and oscillator voltage will increase to compensate the loss that took place on the resistance. So, by this action always V1 will V2 will be constant. So, this is how the loop is maintained. Now, if you want to build the exact circuit for this, we can do like this. We will start from the oscillator, because we have to design oscillator, and then that should energize the LVDT. So, use a transistor based Hartley oscillator. For example, we can have this, then we have the output here, that is actually one transformer we can have, that can be a primary of the LVDT, that is secondary here, secondary here. So, this is a primary of LVDT, and then that is the core, and this is S1, secondary 1, secondary 2, and this is the transformer that we have, and in this we will also wind one more winding and then connect this. So, this is the basic circuit of the Hartley oscillator. I will explain this now. Now, we complete the circuit so that it becomes a working circuit. To make the circuit to work, what we do is we will have to rectify into DC. So, I do this. I will also do the rectification of this voltage. Now, I want to filter it, so I do the filtering here. Similarly, I do the filtering here. So, if this is grounded and this is grounded, then I will get V1 here, V1 here, and then V2 here. Now, I have to add this V1 plus V2. So, the comparator I can use here. So, I have these two voltages can be added here. This I can connect to the, I will only have one RC to filter the oscillations. So, I will have this is given to the to be given to the reference voltage. Now, this is the basic circuit. What we are trying to do is that we are rectifying this and getting a DC voltage here, rectifying this and getting a DC voltage here. Now, there is one issue in this rectification, mainly because this we are using a diode here. If you are using a diode here, then this will drop 0.6 volt all the time, and then this 0.6 volt also changes with temperature. So, it is 0.6 volt at 25 degree C. As the temperature increases, the voltage drop across this decreases by 2.2 millivolt per degree C. So, higher temperature you will have only smaller voltage across this and smaller voltage across this. So, the simple circuit what we are aiming we has this drawback. So, we will address this issue little later. Now, if we take this voltage, what we are trying to do is I am trying to compare this voltages, say R1 here, R2 here, they are equal, say R1 is equal to R2, and assume that this is kept at say 2.5 volt or 5 volt. So, in case if the sum of the voltages increases, then this will increase and that will make the output decrease. The output decreases, then we know that voltage at this point will decrease, and then the once voltage at this point decreases, the amplitude of the oscillation that is coming here also will decrease, and the same voltage is applied to the primary of the transformer. So, the amplitude applied the excitation voltage of the LVDT primary also decreases. So, by this action, that is if the voltage decreases here, then automatically this voltage increased, and then that increases the amplitude of the oscillation, and the excitation voltage also increases. In case if the V1 plus V2 decreases, then this is less, this is more. So, output goes high, and then the amplitude of the oscillation increases, and further that will increase this. So, like that the loop can stabilize and work, except that, as I said, the issue with this diode that is to be solved, that we will do it little later. Now, let us concentrate how to design this oscillator circuit, which is a Hartley oscillator. Now, if you see the actual circuit, you have these two resistors which are used, so it is R1 and R2, R1 and R2 for biasing actually. So, assume that I have kept this point, say this point at say 1 volt, then I know that this point I have to stay at 0.6 volt. So, I can select R1 R2 such that at some voltage, say for example, at at 10 volt here, at 10 volt here, I want to get here 1 volt. So, I can select R1 R2 to get 1 volt when the input voltage is 10, and if it is 10 then you will have 0.6. So, as soon as I switch on, then the voltage at this point increases, that increases the current through this, that current is flowing through this. So, as the current increases, the magnetic field across this increases. So, increasing magnetic field produces a positive voltage here, because we adjusted the dot polarity like this, and the magnetic field increases, then the current increases, the magnetic field increases, and that produces a positive voltage here. When the positive voltage comes here, that voltage added along with the DC, the whatever voltage that is coming here from here, that is added with the DC voltage. So, you get a increased voltage. When the voltage increases, then this voltage also increases, then this current increases here, and then further increase in magnetic field is expected. So, the first step is that upon switching on the first step is that the emitter current increases. The emitter current increases. Because of that increase in current, this produces increasing magnetic field on this coil. This produces increased magnetic field. Magnetic field in the coil. So, this induces this increases base voltage of the transistor. Then once base voltage increases, this increases next, the increase in base voltage, again increases the emitter current, again increases the emitter current. Once the emitter current increases, again magnetic field increases on the primary, again magnetic field increases in the primary. So, increase in the, that is what is the cyclic effect. So, first as soon as switch on, some voltage appears here, that increase the current through this, that current flows through this. So, you have a increasing magnetic field, increase the positive voltage here, that increases this voltage, that increases the current further, that increases magnetic field here, again more voltage comes, and then again current increases, more magnetic field, more increased voltage, like that it will be keep going one after another in a cyclic fashion. After some time you will find that this voltage had increased, and then this current also had increased sufficiently large, and no more increase in voltage possible. That can happen either due to saturation of the core or saturation of the transistor itself. So, in that case, when it reaches that stage, then further increase in current will not produce any magnetic field change in case if the core is saturated. If the amplifier is saturated, this voltage increase, but current will not increase. So, whatever may be the case, then moment the increase in magnetic field stops, then there will not be any induced voltage here. Then this whatever the induced voltage that start decreasing, and this voltage started decreasing, then this current started decreasing, then magnetic field will decrease. Decreasing magnetic field will produce a minus voltage here now, and that will reduce this voltage further, and that will reduce the current further, and that will produce more minus. then like that, then it will reduce here and the further current will come down, like that it will keep reducing, still it goes completely cut off, that when it goes to 0 and this current becomes 0, the magnetic field also will stop. Then again all over it will start, because again because it is 10 volt is there, again the voltage will appear here and then again it will start the current from the positive, like that will keep moving around, and then the oscillation will be occurring, and we can control the frequency of the oscillation by putting the capacitor here, and this the effective L and C decides the frequency of the oscillation, that is f equal 1 by 2 pi L C is the frequency of the oscillation. So, you will get the oscillation. Now, interestingly, if you see if you have more voltage here, if you have more voltage at the at this point, then obviously more voltage will come here and the more bias voltage, and then the unit also will produce more oscillation amplitude also will increase. So, if I increase the voltage here, you will find the amplitude of the oscillation is increasing and you will get more voltage here and the more voltage across the primary of the LVDT. So, that is what we are trying to do. So, here actually the DC voltage converted into AC voltage using this amplifier, that AC voltage is applied across this, and when this voltage is more, you will get more AC voltage here. If this voltage is less, you will get less voltage, less AC voltage here. Now, so that way the primary is energized using this oscillator. Now, we, as we said, the errors associated with this diode problem have to be solved. So, this part of the circuit can be modified in the following manner to remove the diode related error. So, the diode drops first of all 0.6 voltage, and then that 0.6 voltage also not constant, it changes with temperature. So, you will get as if the rectified voltage is changing with temperature. So, to solve that problem, we can modify the rectifier in the following manner. So, we will start from the LVDT. So, if this LVDT primary, then the two secondary voltages are here and the core is here. Now, I rectify this and then I join these two, then both are actually reverse connected. You have this is here, and for this it is sorry, for this the dot polarity is, for this the dot polarity is here and this dot polarity is here. So, essentially when this is positive and at that time this is negative. So, that is what we wanted. Now, take this. Now, what I do is, instead of grounding this, I will actually connect this to a diode and then on Zener diode. Then I bias this by using a resistance. So, I put on resistance here to bias this. We see how much bias current we have to send through this. So, we are instead of connecting this to ground, I am keeping it at some potential here, and that potential actually there is a error here, that potential, this is a diode not a Zener. So, it have a diode and then Zener, say 2.5 volt Zener, and the diode is connected like this. Now, to rectify this, what I do is I will put the diode like this. Filtering I do this, similarly I do this. So, that is coming as V1, that is coming as V2. So, instead of directly instead of simply rectifying using a diode, now we have added this diode and Zener, and then these two diodes, the rectifier diodes which was there earlier only. But then now what we have done is we had made this diode and this diode are actually in the same package and they are supposed to be identical. So, if that is the case, then due to temperature, voltage of this also will drift, voltage also this also will drift, voltage of this also will drift, all will have almost equal drift. In that case, we will show you that the drift due to the diode get cancelled. So, that is our aim that by doing this. So, for example, this is actually 2.5 volt at room temperature, then you will find that this is sitting at 3.1 volt, because this is 2.5 here and 0.6 volt, and this will be 3.1. If this is 1 volt AC, this is also 1 volt AC peak, then you will get at this point 3.1, at the positive side this will go to 3.1 plus 1, 4.1 volt. So, 4.1 comes, then you will get here 3.5 volt. 0.6 is across this. So, if if it is 3.1, you will get 4.1, then minus 0.6, you will get 3.5 volt. Similarly, here on the positive side this will go to 4.1 volt, because you get 3.1 and 1 volt across this, assuming both are producing equal voltage here, 1 volt and 1 volt here, then you will get 4.1 volt here, and this also will give you 3.5 volt. And if the resistance of this very high and this is small, say for example I put here 470k and here about 100 ohms, this is 100 ohms, and I put 470k here, then you will find the same 3.5 volt is coming here and same 3.5 volt is coming here. So, what you got is you got 3.5 here, 3.5 here corresponding to 1 volt and 1 volt here. This is at room temperature. If so, at room temperature, V1 is equal to 3.5 volt, V2 is equal to 3.5 volt. Now, see at 100 degree C, when the temperature of the why we are going up to for industrial use we go up to 80 degree C. So, I will take at 80 degree C, because industrial grade equipment supposed to work in the open air, and the temperature of the open air can go up to 80 degree C. So, all industrial grade equipments are manufactured for minus 20 degree to 80 degree working. So, if in case if the ambient temperature goes to 80 degree ambient temperature, then what is V1, what is V2? So, if you go back and calculate at 80 degree, now at 80 degree what is the voltage that is expected at this point? Now, you will see that if I remove this is 2.5, that remains constant, but then voltage across this what we assume as 0.6 is not at 80 degree, that is at 25 degree C. At 80 degree we have what will be the voltage across the diode. So, voltage across the diode would be there will be 0.6 minus 2.2 into temperature difference. So, the temperature difference is 55 degree. So, that will give you a 0.6 minus 0.11 volt, because 2.2 millivolt into 55 will give you 110 millivolt. So, you have 0.11 volt, that appears that the voltage will be 0.49 volt. So, at 80 degree C the voltage at this point would be 2 plus 0.49. So, roughly 3 volt only, roughly 3 volt. You will get where did I do this? Let go, yeah. So, you will get about this one will come about 3 volt. Then you will find that this is voltage across, this is 1 volt. So, this will come to 4 volt at this point. Then again this also would be only 0.5, then again this will become 3.5, and same thing happens here, this is 4 and this becomes 3.5. That means even though temperature had changed, the voltage drop across this, voltage drop across this, and voltage drop across this all get changed. Net result is voltage at this point remains constant as long as this voltage and this voltage is constant. So, you will get here 3.5 volt, here also 3.5 volt, even at 70 degree or even at any other temperature the voltage will be 3.5 only. So, this will be again 3.5, this will be again 3.5 volt. So, at any other temperature also it will be same, that means V1, V2 will not change with the temperature. The temperature drift problem is compensated by adding this adding the diodes to the adding the compensation diode, that is this diode. By adding this diode we have removed the temperature drift problem. Now, this zener is mainly added to push the voltage to one side, because by adding this 2.5 this already gone to 4 and you will not get minus voltage, and that is good because most of these diodes have a low voltage capacity. So, that is also good, plus we also need this zener for other purpose. So, we have put even without this zener also it can be done, by directly grounding also one can remove the voltage, but the floating one side positive completely gives a better result. So, we have done this. I will show you the usage of this diode little later. So, this voltage now can be summed up as you set in the comparator amplifier. So, what you do is now I will take the two secondaries here. So, if you look at this, you will add this and then I add the zener voltage, then we had this, the bias voltage, then I add these two voltages in the comparator. So, it is to discharge, I resistance is put here. Then these two voltages can be summed up at this point, minus, then V reference we need, that this itself can be utilized for V reference. So, I put a divider here and then connect the V reference to this point, and this can be connected to the oscillator, that is actually the oscillator, we already discussed about this. So, you get the so that solves the both the problems, that is we have solved now the temperature problem of this diode, rectifier diodes, and then we also solved by giving the feedback and maintaining V1 plus V2 constant, the temperature change, the temperature induced error due to the resistance drift of the LVDT, because if we take this is the LVDT. So, we have this is the LVDT. Now, even if the temperature of this changes, you will not get any change in V1 and V2, V1 plus V2 will be constant. Now, if I see this V1 here and V2 here, if I see the difference between V1 and V2, that will truly represent the displacement given by the core, because you have the core here. If the core moves, now you will find V1 and V2 are changing. For example, if I move the core upwards, V1 will increase and V2 will decrease. If I go downwards, then V1 will decrease, V2 will increase, and this V1 minus V2 now depends only on the movement, not due to temperature change of this or temperature change of these diodes. So, this is how the LVDT to be energized first. Now, the V1 V2 can be utilized to produce a current. Now, that can be done by a simple circuit. What we can do is we can put a current transmitter or even convert a voltage into current. For example, if we have this V1 here and V2 here, if we can even put a follower. So, this is V1 and then I have V2. So, this is V2. So, the V1 V2 for example, I can convert into difference in voltage that can be done with a difference amplifier. So, you will get here V1 minus V2. So, this voltage represents the displacement. So, this also can be done, or we can convert this into a current V1 minus V2, that is you are also getting here V1, here V2. This also can be converted into current, that can be done using a current transmitter. So, I can have a current transmitter here. I can have a current transmitter like this, I can put this. Then all that I do is that I have a V1 here and V2 at this point. Now, that actually should be converted into, the difference should be converted into current. Now, one possibility is that I can apply this, for example, I can have V2 increases, then I can also put for example 0 adjustment part here. So, we have V reference here and this can be connected to this. Then the V1 can be connected here and then the output feedback can be given from here. Now, this gives you the current through this. Now, depends on the difference between V1 and V2. Say V2 minus V1, V2 minus V1 gives you the current. So, this is for, it can be used for current transmitter. If you look at this how it is working, we can explain this by putting the values. For example, I can put here say 100K. 100K here, 100K here. For example, if I have here say 1 volt. Now, for simplicity, for example, assume that this is kept at 0 volt. If it is kept at 0 volt, then you will get at this point V2 by 2, and this has to be V2 by 2 because plus has to follow this one. So, obviously, if this is more, then you will have the current flowing here, current flowing here. If both of them are equal, V2 minus V1 are equal, then you will find this is V2 by 2 with this V2 by 2, then the voltage across this have to be equal to this because the same current is flowing. And you will find if V2 minus V1 is equal, then if this contribution is not there, for example, I connect this is simply here, then this becomes a difference amplifier, you will get 0 volt at the output. Now, or we can explain like this, that is if we have first I will go to a difference amplifier and explain, then come back to this and explain how this is connected to current. For example, if I take a simple difference amplifier, a simple difference, if this is grounded and then this is V1 and this is V2. If they are equal values, then I get here V2 minus V1 here at the output. Now, if I add this here, say for example, I put a potentiometer and add the voltage here, if this is V reference and if this is V0, then this V0 is as it is coming at the output, that will be V0. So, whatever voltage is given here, that comes as it is without amplifying, and the difference between these two also appearing. If I give a gain, then this also multiplied by the gain, but this will not be multiplied, this will come as it is. That is the function of this one. Now, instead of connecting it to this here, if I connect to output somewhere, see as we did in this case. For example, we have connected the minus, instead of connected to the output, we have connected to this point. So, now voltage at this point actually applied to this divided by 2, because whatever voltage is there say V0 here, that V0 is actually coming as half of that. So, V0 by 2 will come. In case if the current increases, in this case V0 will increase and that will increase this voltage, because V0 half of V0 is appearing here. Similarly, V1 is there, V1 also will have, assuming this resistance is very small, V1 also will apply a voltage at this point, that also again half. So, voltage at this point is V1 by 2 and V0 by 2. So, voltage at minus terminal is at V minus at V minus terminal, at an inverting terminal, the voltage equation is V1 by 2 plus V0 by 2, and that is supposed to be equal to voltage at plus terminal. So, voltage at plus terminal is V2 by 2 and the constant voltage, so by 2. So, at plus terminal the voltage will be V2 by 2 plus VR by 2. That is, if I assume this is VR, this is assume that I have kept full voltage, then you get this is V2 by 2 and this is. So, these two must be, both must be equal. So, essentially if you find that V1 by V1 plus V0 will be equal to V2 plus VR. So, if I take this outside, then you will get V2 minus V1, that would be equal to I bring V1 this side and keep V0 minus VR actually. So, since VR is fixed, so V0 is proportional to V2 minus V1. So, you will get the difference will produce a voltage V0. So, the current would be V0 by R. Suppose the current is if the resistance R, so the current will be V0 by R. So, that way V2 minus V1 can be converted into a current. So, with this I will stop today's class. So, we will discuss more about this tomorrow, how to use LVDT and so on in the next class. Thank you.